In this video, I'm going to teach you the Evans rules for approximately drawing the root locus of a feedback loop. Rules that, as you know, can be derived from the magnitude and angle conditions you're already familiar with. Now, it might seem useless to learn how to sketch root loci by hand, given that we have software tools such as MATLAB or Octave which do that work for us. However, we keep teaching them because knowing how to draw the root locus somehow helps to develop your intuition about the open loop closed loop relation, and also it allows you to guess in advance the effects of your actions in designing the controller, or the effects of changing, for example, the poles and the zeros of your controller. So let's go with those rules. The first one defines the branches of the root locus, their number, their origin and end, and their symmetry. Now, each branch, as you know, is formed by all the possible positions of one closed loop pole. So there have to be as many branches as closed loop poles. Or maybe another way to say that is that the number of branches is given by the order of the characteristic polynomial. So, for example, if we have this characteristic polynomial as cubed plus bs squared plus cs plus d equal to 0, here any root locus based on this characteristic polynomial must have 3 branches, and that is regardless of what parameter we consider or we choose as the varying parameter, which parameter we choose as our v times f of s equal to -1, which one we choose as our v. Well, the number of branches has to be either n or m. N is the number of finite poles of f of s, and m is the number of finite zeros of f of s, and the number of branches is the maximum of n m. Also, we know that branches start at the poles of f of s, and at that point v is equal to 0, and the branches end at the zeros of f of s, in which v is equal to either plus or minus infinity, because if there are, for example, here 3 branches, there are 3 branches for the positive root locus and another 3 branches for the negative root locus. Well, the three of them finish at the poles when v is equal to infinity, and the other 3 finish at the poles when v is equal to minus infinity. But what happens when there is a different number of poles and zeros? Well, in that case, the root locus can start or end in poles or zeros at infinity. For example, if f of s has more finite poles than zeros, such as in this case v times 5 times s plus 2 over s times s plus 1 times s plus 3. In this characteristic equation, f of s has 3 finite poles and only one finite zero. So we have this pole, this pole, this pole, and this zero. The positive root locus has 3 branches. One of them begins here and ends in the 0. And here we have one branch here that tends to infinity following certain asymptote, and this other branch tends to infinity following another asymptote. So another way to see that is that they end in the zeros of the system, but in the other two zeros of this function, which are infinity and infinity. And if the situation were the opposite, I mean, with the poles, with the previous poles as zeros now, and the previous zeros as current poles, we would have here a 0, another 0, another 0, and a pole. The positive root locus would be this part here and this part here, but this branch would start here and would end here, and some branch would start at infinity and it would end in this pole, and some other branch would start, and the third branch would start at infinity and would end in this other pole. Actually, I've only drawn the positive root locus. The negative root locus in this case would be this branch, this branch, and this branch. So again, the branches would end at infinity, and in this case, this branch would come from infinity. This branch goes to the right, and this branch comes from infinity to the 0. Finally, branches are symmetric with respect to the real axis. Well, that's quite obvious, since, as we know, when we have a complex conjugate pole, a complex pole, also its complex conjugate is a pole of the system, and that leads to the symmetry of the root locus. Okay, let's go to the second rule. Points in the real axis. What you have to know is that all points in the real axis belong to the root locus, and the only thing you have to do is to find out which ones belong to the positive root locus and which ones belong to the negative root locus. And the rule you have to apply to do that is very simple. Points which are to the left of an odd number of poles of an odd number of poles and zeros of f of s, I mean real poles and zeros of f of s, belong to the positive root locus. And points which are to the left of an even number of poles and zeros belong to the negative root locus. So again, an example to make things clear. Here it is. Well, in this case, we have a 0 at -1, a pole in the origin, and another pole at -2. So points belonging to the positive root locus are these ones and these ones, because they have this part has one pole or 0 to the right, and this one has 3 poles and zeros to the right. And points in the negative root locus are all these points. Actually, this is almost all the root locus. The only part left is this branch here, or this part of the branch here, that we'll learn how to draw very soon. Okay, and finally, the last rule we're going to learn in this video is the asymptotes. Those asymptotes that the root locus follow when there are more finite poles than zeros, or more finite zeros than finite poles. So all those asymptotes intersect at certain point called the centroid. The centroid. The centroid of the asymptotes, which is given by this very simple formula. Sigma is the sum of all the poles of f of s minus all the poles of, sorry, that would be 0, all the zeros of f of s over the number of finite poles minus the number of finite zeros of f of s. And in this equation we can actually use only the real part of the poles and the real part of the zeros, because the imaginary parts cancel out. So let's do an example. For this characteristic equation, the centroid sigma a is the sum of all the poles, so 0, sorry, this was supposed to be 2, so 0 minus 2 minus all the zeros, which since there are no zeros we don't have to subtract anything, over the number of poles, that's 2, minus the number of zeros, that's 0, so this is minus 1. The centroid of the asymptotes is at minus 1. And we now have to know the asymptotic angles. Phi sub a, which is given by 180 degrees times k over the absolute value of n minus m. And here k can be any natural number, 0, 1, 2, 3, 4, 5, up to 2 times n minus m minus 1, which actually you don't need to apply, because the only thing that this is telling us is that if we have 2 more poles than zeros, then we have to find 2 asymptotes for the positive root locus and 2 asymptotes for the negative root locus. Okay, you'll get that as you do exercises. In this case, 0 and 2 and all the even numbers give the asymptotes for the negative root locus, and 1, 3, 5 and all the odd natural numbers give the asymptotes for the positive root locus. So in the same example we were working with, phi sub a is, for k equal to 0 we have 0 degrees. For k equal to 1 we have 180 times 1 over 2, and that's 90 degrees. For k equal to 2 we get 180 times 2 over 2, that's 180 degrees. And for k equal to 3 we get 270 degrees. And we don't need to calculate any more angle, because we know that there are 2 asymptotes for the positive root locus, this one and this one, and 2 asymptotes for the negative root locus. So if we draw those asymptotes, recall that the centroid is at minus 1. Well, I shouldn't have used that color. Let me use yellow. This is the centroid, and the asymptotes for the positive root locus are these ones, and those for the negative root locus are these two ones. Well, this is quite simple, and yet once you get used to drawing root loci, you stop using this formula, because what you do is, okay, there's one more pole than zero, or one more zero than poles. Then the asymptotes for the positive root locus, the only asymptote actually is this one, and the only asymptote for the negative root locus is this one. Now, if there are two more poles than zeros, we have this situation. Okay, I'm mixing up colors here. Blue is for positive, and green, no, and green is for negative root locus. So if there are two more poles than zeros, or two more zeros than poles, the negative root locus has these asymptotes, and the positive root locus has these asymptotes. If there are three more poles than zeros, or three more zeros than poles, the positive root locus asymptotes are distributed according to 120 degrees in this way, and the negative root locus asymptotes are distributed like this. And for a difference or an excess of 4, let's see, these are the positive root locus asymptotes, and these are the negative root locus asymptotes, always evenly distributed along the 360 degrees. Okay, that's all for now. In the next video we'll continue with another 3 rules for drawing the root locus.